All right. Now we're going to start looking at multiple objects connected in a system. So we know that from Newton's third law, anytime two objects interact, there will be those equal magnitude forces in opposite directions. And while those definitely exist and can affect the motion of individual objects, we know that a whole system couldn't exert a force on itself. So we'll be looking at these external and internal forces between objects within a system and use that to analyze the motion of each object. But we'll be dealing with systems where all of the objects are connected somehow by a string or not slipping on each other, something that forces their accelerations to match. And if that's the case, then we have this sort of rephrased Newton's second law that says the acceleration magnitude of any object in the system will be the total net force on the system, so nothing internal, divided by the total mass of the system. So we will be just taking objects and just condensing them down to a single box, is how we like to do it. Now, you could also just write F equals ma equations for all the objects, and it'll all work out. But and that's helpful to find the internal forces, but usually our strategy will be find acceleration by putting everything in a big box. So what I mean by that is you draw a big bounding box around the system and know that anything inside the box cannot contribute to the net force on anything inside the box. So, notably, the things that cancel all the time will be contact forces between objects or tension forces. So, nothing inside the box could contribute to the net force. Things that definitely will contribute to the net force are things like unbalanced weights or frictional forces, anything like that. So, to determine what is actually going to happen, you have to define a positive direction and do the whole help minus hurt idea. And that gets you your net force. And then you can find your acceleration by dividing the help minus hurt net force by the total mass. So in this case, which we will do in much more detail, it's okay if we don't totally understand what's going on here yet, is for this system, if we're assuming it's going to accelerate this way, we have an M2G that's trying to pull it that way, and we have an M1G that's trying to pull it the other way. So the net force would be the clockwise force minus the counterclockwise force. So that's why that is our numerator. And then our denominator would be the total mass of the system. So the acceleration is just F net on the system divided by the total mass. We'll definitely start with some simpler examples. All right, a block of mass 3m and a block of mass 1m are in contact on a frictionless horizontal surface. A horizontal force F is exerted on the 3m block, and the two blocks move together. So when we see something like this, this is our indicator that we have the same acceleration. So what is that acceleration of the two block system? So anytime you want the acceleration of the system, we say draw the big box. There are definitely other methods of doing this where we look at the forces on each block, but it's easiest to find acceleration just by doing the bounding box. So the acceleration is just F net on the system divided by the total mass. So in this case, I have a force F that is the only unbalanced force from outside. So of course there are some 3mg and an mg and then a normal force and a normal force. Those aren't unbalanced, so I'm not including them in the net force. And then what's the total mass of the system? Well, I have 3m and 1m, so 4m. So that would be my acceleration. Now let's draw and label the forces exerted on each block. So it makes sense for my 3m block to get 3 units of downward weight force. And my 1m block would therefore just get 1 unit. So that means the normal force, the force from the ground, on the 3m block would have 3 units, and on the 1m block, it would have 1 unit. But notice neither of these blocks are accelerating as I have it drawn, which means that there must be another force. So what is that force? Well, forces can only go on objects if there's an active touching happening. So I can include the F on the 3m. I can for sure do that. Because that force is touching. So there would be a net force. But now we got to think about what's happening with the 1m block. So what is pushing the 1m block? Well, it's not F, because F is not touching the 1m block. What is touching the other block? It's the 3m block. So there's actually going to be a contact force. So there's a force that is going to push the m block to the right. I might call that F from the block. Call it blocks. And why did I call it F blocks? Well, Newton's third law. So if the 3m block is pushing the 1m, the 1m must equally be pushing back on the 3m. So there will also be an F blocks this way. I need more space. All right. Let's derive an expression for the magnitude and direction of the normal force that the block of mass 3m exerts on the block of mass 1m. Well, we know that F net on mass m would be equal to its mass, 1m, times its acceleration. The F net on the 1m block, it is literally just F blocks. So there would be m times the acceleration of the system, we said was F divided by 4m. So the force on the block 1m would just be 1/4 F. And this is directed to the right. So we could do this whole thing to determine the magnitude and direction of the normal force that the block of mass m exerts on the 3m. We could do this. Why not? I mean, we know what it should be, but yeah, let's actually do it. So the net force on the 3m would be equal to its mass times its acceleration. The net force on the 3m would be the forces helping it accelerate, which is F, minus the forces hurting it, which would again be the force on the blocks, or which I'll say on 3m. That's going to be just 3m times the acceleration, which was F over 4m. And if we do that, we get F minus F on 3m is equal to 3/4 F. So we would get that the force on the 3m is just 1/4 minus 3/4, which is, unsurprisingly, 1/4 F, and we said this force was left. Now, did you have to do this? This was a determined statement, so I really intended you just to do this with third law. Equal yet opposites. All right, suppose there is now a kinetic friction coefficient. Derive an expression for the acceleration of the two block system in this case. So now, this was the big block. Now we're saying there's a kinetic friction coefficient. So we're still pushing with F, that is still an external force. But now we have a kinetic friction force on the 3m, and we have a kinetic friction force on the 1m. And those are not internal forces because the ground, the entire Earth, is not part of this little bounding box. So we can just use our fact that acceleration is just going to be the helping forces minus the hurting forces divided by the total mass of the system, which would be the force F is still the only thing helping, and there's two hurting forces. There's the kinetic friction force on the 3m, and there's the kinetic friction force on the 1m. Total system mass, still 4m. So what would be our frictional force? Well, again, this is just going to be mu times normal force on the 3m, and this would be mu times normal force on the 1m. And since we're on a flat horizontal surface, these will just be their respective weights. So the acceleration would be F minus the quantity mu times 3mg minus mu times 1mg divided by 4m, and this can be simplified to F minus 4 mu mg divided by 4m. We could simplify this more, but I'll keep it as this. No, we'll do it. So it's F over 4m, which was the original acceleration, minus mu g. So as long as F over 4m is bigger than mu g, we accelerate to the right. This is another classic scenario. This is called the block train, where we have just a bunch of blocks connected to a string. They're going to get pulled to the right. Everything stays connected. We want the tension in each chord segment. So we have this segment, this segment, this segment. So tensions are not all equal because it is not the same string, right? There's a gap between this segment and this segment. It's not just the same, so it could be different. So what we know for sure is that each block will have the same acceleration because this is a connected system where the string is just going to be a fixed length, so it's got to be same acceleration everywhere. So what that means is that there will be different forces in different spots to get that same acceleration. So for example, at A, we just have to supply some sort of acceleration to the 2 kilogram. At B, we got to accelerate the 2 and the 3. And at C, we got to accelerate the 2, the 3, and the 4. So the tension actually increases left to right. Because each block has to have the same acceleration, but different points of the string, different string segments have to accelerate bigger masses. So A has to deliver some acceleration to a 2 kilogram. B has to deliver an acceleration to the 2 and the 3, and then C has to do the 2, the 3, and the 4. And since F net equals ma, it requires more force to deliver the same acceleration to more mass. And that's what I said here, right? We're just accelerating more mass as we go to the right. So what is the acceleration of this system? Well, the acceleration of the system is just going to be the net force on the system divided by the total mass. So what is the net force on the system? Well, the 3-block system, I can just do this. So the only unbalanced force, because there is still mg and normal force on these axes, that's not doing anything, no friction. So the net force would be the 18 newtons, and the total mass would be 2 plus 3 plus 4, which is 9. I see why I did that, because we get a nice clean acceleration. All right, let's label the forces on each block. All right, so we'll kind of use my intended thing with the tick marks here. So 2 kilogram, I'll give you 2 units. 3 kilogram, I'll give you 3 units. 4 kilogram, I'll give you 4 units for each of their weights. Then for their normal forces from the ground, of course, they're just going to be a balancing force. Fn, Fn, Fn. And now let's look horizontally. So 4 kilogram, we said is getting pulled with the most tension, so I might give you that much. We'll call that the tension at point C. It's just getting pulled by the tension at point C. There's also a rope at point B pulling on it. There will be a tension at B. Then by Newton's third law, that tension at B will be the same, but in the opposite direction. And then there will be an even lower tension at A. So something like this. Because the sort of intermediate ropes will be pulling on both the masses on either end. So get this. Because we said the tension should be greater when it's accelerating the larger chunk of the train. That's why we can have this picture. Let's calculate everything. What is the tension connecting the 2 and 3 kilogram? What is the 3 and 4 kilogram? Okay. So here's where we'll just do some F net. So if we want the tension between the 3 and the 4, that would just be, we can pick our favorite mass to find F net on. So let's do F net on the 4 kilogram is going to equal the helping forces minus the hurting forces. And we also know that we can write net force as mass times acceleration, which was 2 meters per second per second. So what is helping the 4 kilogram accelerate? The C tension. What is hurting the 4 kilogram accelerate? It would be the B tension that we want. And this looks like a problem because we have two unknowns, but technically we don't, because we know that the tension at C, since this is a singular connected string, would be 18 newtons. So we'd get 8 equals 18 minus TB. So the tension in the B segment is 10 newtons, which is less than 18. So we should decrease again when we do the 2 kilogram. So you can actually pick either. You will get the same answer. Notice how my 2 kilogram block looks to be the simplest one to analyze because there's only one force, so I don't have to do any subtracting. You will get the same answer. So I want essentially the same thing. F net on the 2 kilogram is equal to the helping forces minus the hurting forces. And MA is just 2 and 2 here. What's helping the 2 kilogram accelerate? Well, that's just TA. What's hurting it? Nothing. Nothing. So TA would be equal to 4 newtons. And we can quickly check that all of these work because my net force, or sorry, my acceleration should work out to 2 meters per second on all of them. So here our acceleration would be 4 newtons divided by 2 kilograms. That's equal to 2 meters per second per second. No units to save space. Here, we said TB was 10 and TA was 4. So 10 minus 4 over 3, that's equal to 6 over 3. That is 2. Then here we had 18 minus 10 divided by 4, which is 4 over 2, which is 2. So we see that it does work. All right, this is our last scenario of the main part here before we get on to pulleys. And this is what I just call the block stack. So we are pushing a block, and then there's another block on top of it. So we have a book that is on top of a crate in this scenario. I am pushing the bottom block, and the objects are moving together. And as shown by the picture, like I implied it at least, this is a larger mass. All right, let's draw the forces. So first we have our book. This one's pretty easy because the book, it's just going to have some sort of a weight. Then it's going to have a normal force. And then we are given that these are accelerating to the right. So we'll think about why that's happening now. So I think we'll come back to it actually. Let's do the creative mass M. So we'll start with like a bigger weight force, Fg. And now we have to start considering kind of the intermediate forces here between the objects. So first of all, the fact that these two crates are touching means, yes, there is a normal force on this book, but it is from the crate. And Newton's third law says that there's always a pair. So if the book is getting pushed up by the crate is getting pushed down by the book. There's actually going to be an equal normal force. So I need to rearrange these. So there'll be an equal normal force on the crate by the book. So therefore, there should be a force from the ground on the crate that must balance both of those. So this Fn represents the Newton's third law pair between those surface contact points. And then this F ground, and notice the ground has to balance the weight of both, which should make sense. So if you have any of these block stacks, the sort of total normal force of the bottom has to balance the weight of the whole stack. All right, so now we have to deal with what is causing the book to accelerate, because currently it's nothing. So acceleration, that's good for the crate, but we're given that this stack is accelerating. And it does say that there's friction between the crate and the book. So there's friction on this surface. So what would be causing that acceleration? Well, it must be friction. So this is the strangest part of this question, that there is actually a accelerating friction, which we haven't seen that before. So there's an accelerating friction. And actually, since the blocks are not moving relative to each other, they are moving relative to the ground, but the book is not sliding forwards or backwards. It's just stuck in place. It's actually static friction. And by Newton's third law, there's an equal and opposite static friction force here. So this is quite a lot going on here. But we can check that everything works out because the book accelerates, the crate accelerates, and we have all of our forces between the objects are equal and opposite Newton's third law pairs. All right, let's find the acceleration of the system when the book is not slipping. Well, this is the easiest part of this question because we just want the acceleration. So put everybody in a box. Acceleration is just F net over m total. The force is F. The total mass is m plus little m. There exists a maximum value of the pushing force such that the book does not slip. Justify this. So why is it that if we push too hard, the book will begin slipping on the crate? Well, anytime we're thinking about maximum values and friction, we should be thinking of the fact that Fs max equals mu s times normal force. So static friction is a maximum value. So the fact that the book is being accelerated to the right by static friction means that if we're accelerating so fast, that would mean the net force needed is so big that we can't actually get that net force from static friction. So we're saying that the objects move together due to friction. And if the net force in the system is too large, that means that the required acceleration can't be generated due to static friction alone because static friction is capped. So you need more of a net force on that book than static friction can generate given its coefficient. All right, so now we will do a expression for F max. So what is the maximum force that we can push the crate with such that the book does not accelerate? So we're going to solve this using the same principles we've done before, where we're going to use the fact that their accelerations are linked, which is usually the key with these problem types. Right, so we have determined the fact that A of the book is equal to A of the crate, which is equal to F over m plus m. So given the fact that the limiting factor here is going to be the book that's slipping because that is the thing being accelerated by static friction, we could look at a Newton's second law equation for the book. So F net on the book is equal to its mass times its acceleration. Sorry, we should do help minus hurt. I usually like help minus hurt on this side. So F net is ma Static friction is actually helping the block accelerate. Nothing is opposing its motion. The acceleration we said was going to be equal to F divided by m plus m. But in this case, we're looking for this max force F. And then static friction. Well, if we look at our diagram over here, we see that there's nothing interesting happening here. So Fs is going to be equal to Fs max, which is just going to be mu times the normal force, which is mu mg. Little m for the, so I want to make that clear. This is equal to mu times little m times g. So this gives us F max would be equal to, let's see, the little m would cancel, and then I need to multiply by m plus m, so I'd get F max would just be equal to m plus m times mu g. So it does make sense that we're limited by this frictional coefficient and the masses that we have to accelerate. Now we want to graph the different accelerations as a function of the force. So the easy part is before F max, because the acceleration is going to be just a system acceleration that everybody shares before we have reached that maximum value. And as we increase the force, we increase the acceleration. Newton's second law is linear. So here we have the block and crate sharing accelerations. Now, after, the relative magnitudes are going to depend on the friction coefficients, but usually it's fair to assume that kinetic lower, static. So what that means is the crates begin to slide, and the force of friction on the book is now going to be kinetic friction, and it's constant because kinetic friction is constant. It doesn't matter how hard you push, kinetic friction is constant. So we're going to get the book acceleration as a constant lower value than its maximum due to that kinetic friction regime. And then for the crate, I can keep pushing the crate. I'm still pushing the crate, so it's still going to accelerate more and more and more. And if we're being really precise, the slope should change depending on when that block slides off. But slope should actually go up because the friction exerted on the crate is actually lower now. Could this be the hardest graph in the entire course? Could be. This is a really crazy graph. Also, there's just a chance that it's wrong, but I'll probably have caught that if it is. Doesn't get easier. This is also one of the harder comparisons we have to make. Suppose the forces then applied to the book instead of the crate indicate how F max will change. So what if instead, actually this is not as bad as I thought. What if instead we apply the force to the top block instead of the bottom one? So once again, we have to think about why there was a max value of F we could have. There's a max value of F we could have because static friction had to accelerate somebody and it capped out. So here, static friction's accelerating the big crate. So actually, this is not as hard as I thought it was. F max is greater when the force is applied to the crate, because if you're applying the crate from the book, static friction has to accelerate the heavier object, so static friction caps out at its max value first, because it's accelerating the heavier mass. So the max value is reached sooner when F is applied to the book, since static friction is responsible for accelerating the larger mass. Yeah, that graph is crazy. Can't believe that. So now we'll look at a whole genre of problems where our objects are going to be connected by pulleys. So we're going to make some nice assumptions here that our pulleys are ideal, meaning they're massless and they don't contribute to the inertia of the system. So what they do serve the function of is changing the direction of tension forces. Because we said that in an ideal pulley, the tension's the same everywhere. So a pulley can serve to just move that direction around. And since we assume that these pulleys have no mass, all the forces on any pulley must cancel, or else the pulley would be infinitely accelerating. So just to show kind of some of this pulley stuff, we're going to start with a scenario known as a Bosun's chair, which is, I think of it as like a window washer harness type thing. So here we just have a person suspended in like a, almost think of it like an elevator type thing with a pulley, and person B is on the ground. It says person B pulls on the rope with a downward force T on the rope, which causes person A to rise at constant speed. So if we just do our tension tracing, this is just a single rope, so it's going to be the same everywhere. So that T is being supplied here as well. Person B will experience an upward force T from the rope. Justify this claim. Well, person B pulls down on rope, so rope pulls up on person B. This is just Newton's third law. So since they're pulling down on the rope pulls up on them, equal and opposite, Newton's third law. Force time. So person A and the chair, of course, they have a weight, and they're being pulled upwards at constant speed, which means the tension is just balancing. Now, person B, they have a weight as well. I don't know if it's the same or not. And they're pulling upwards. Actually, let's make it less. I think we make it less. No, greater. Let's make it greater. Why not? They're pulling up with this force T. They're pulling down on the rope, so the T pulls up on them. So there will be an upward force T on the person. And then the normal force just makes up the difference. Kind of contrived that to give us a non-zero normal force, but whatever. Assuming the mass of person A in the chair is 80 kilograms, calculate the required force T. Well, this is really easy from our free body, right? We just see that T is just equal to mg of the person. So it's 80 times 10, so 800 newtons. What happens to person B if they lift the chair, but person B has a mass of less than 80 kilograms? Justify your answer. So if we see what's going to happen, if person B is very light, they would actually be pulling upwards. They'd have to generate more upwards force than their weight to pull that person. So the tension force on them would actually be greater than their weight. So they lose contact with the ground. So if you try to pull them, you're going to actually start getting lifted off the ground because you've pulled down with a greater force than your own weight. So Newton's third law says that that tension force equal and opposite would be bigger. Now, this is the more common scenario with the Bosun's chair, where it's actually just a self-propelled chair, where the person is actually doing the pulling. So the person pulls down with T nu. So this is T nu, meaning we can trace T nu all the way back here. And also, we can't forget the fact that since person A pulls down with T nu pulls up on the person. So there'd also be a T nu this way. So we see that there definitely will be a weight force still. That didn't change. But now what changes is that there is a T nu on person A from their Newton's third law pair. And there's going to be a T nu from the wraparound on the Bosun chair. So what's the new pulling force T nu? Well, we see that two T nus together balance the weight of the person. So it's exactly half of what it was before. So you can actually lift yourself with half of your weight if you have this sort of setup. And that's another reason we use pulleys, is they allow you to multiply this force when we deal with these attachment points, which we'll see here. So here's some pulley tracking. We just want to rank the magnitude of the tension we needed to sort of lift these masses at constant speed. And they are all the same. So first of all, do the rope tracing. That's really easy. So scenario 1, we get exactly T1 that pulls the M, meaning the required force would just be mg. This pulley is essentially doing nothing. T2, we track this. We do see that it is the same string, so the tension will be the same everywhere here. So this will be a T2. And this will also be a T2. So notice here that this pulley is getting pulled upwards with 2 copies of T2 instead of just 1. So we need only half the force here, because there are 2 connection points right here. Now for T3, we can do the tracing again. Same continuous rope. Here's a T3, here's a T3, here's a T3, here's a T3, so there's 4 of them. So this actually makes it 1/4 mg. And how does this actually work? Well, it works because these little connection anchors cancel those upward lifting points. So there'd actually be 2 T2s down here balancing these 2 T2s, and then it's just duplicated by symmetry here. Now this is the actual main case to know, is these Atwood machines. So we'll end with these, where we'll deal with the regular Atwood and then all of its cousins. So let's think about what's going to happen in this system here. So we want the direction of the 2 mass systems acceleration, which means if we want the system acceleration, we big box it. And we are given that the big M is bigger than smaller m. So there's a big mg, and then there is a little mg. So what we see is happening here is we want to know clockwise or counterclockwise. So this mg, the big mg, is trying to get the wheel to go this way, and the little mg is trying to get the wheel to go this way. So we have a clockwise force pulling me this way, and we have a counterclockwise force pulling me the other way. So as a result, we said the mg is bigger for the big M, so we get clockwise acceleration. The weights are attempting to accelerate the system in opposite directions, is what I said. What am I doing? I'm trying to erase this because it's annoying me. So we said that they're trying to accelerate in opposite directions here. And since the tension force is internal, it's really just looking at the weight differences. Like there's a tension here, but there's also a tension here, so that cancels. And the net force is therefore from the big M, so we go clockwise. All right, let's draw our forces. So on the little m, I'm going to give it a little mg. And for the big M, I'm going to give it a big mg. And we know that there must be an equal tension everywhere because it's internal and canceling. So we know that the little m, as it's rotating clockwise, the little m must be lifted up and the big M must be lifted down. So the tension must exceed the weight here, and it must lose to the weight here, which means that I need to make my mg bigger. And that's sometimes something you run into when drawing these free bodies. Okay, you don't have to think that you should know the exact numbers going in. Like, we can do it on the fly. All right, by writing a system of Newton's second law equations, derive an expression for the acceleration of each mass. So this says use Newton's second law. So we're going to say that acceleration is clockwise. So F net on the little m is going to be equal to help minus hurt. F net is ma. What is helping the little m accelerate? The tension force. Is that is it helping it go clockwise? What is hurting it? Its weight mg. Then similarly, F net on the big M is going to be help minus hurt. MA with the big M. What is helping the big M accelerate? This time it's its weight mg. And what's hurting its acceleration? That would be the tension. So notice we have sign differences here. Even though the directions of the forces were the same on our diagram, again, we're thinking about counterclockwise versus clockwise. So anything that's going counterclockwise is negative. Anything that goes regular clockwise is positive. So now we got to solve this to get the acceleration. So we said little ma was equal to ft minus little mg, and big ma was equal to big mg minus ft. So notice that there's a plus tension and a minus tension, and I don't care about tension. So I can actually just add these equations together and eliminate tension. And that's not a coincidence that that works. That is a third law internal force canceling consequence, right? That we do expect that actually. So we can, these both have a in it, so we get like terms of little m and big M, both have an a. And then big M and little m are being subtracted here. So our acceleration would be big M minus little m times g over big M plus little m. Let's find the tension in the string now. So we can pick any equation now to plug back into to get that tension. We can use this one maybe. Little ma is equal to F tension minus mg. So ma, where a was this. So ft would therefore just be equal to mg plus that. And let's see, I'm sure we can simplify this. You could definitely just leave it like this. Notice it's equal to the weight of the little mass plus some extra stuff that'll be positive. Yeah, I'm not going to simplify this. I think this simplifies to like, it's something like this. It's something close to this, I feel like, as like the tension in the string. But we will, don't take my word for that. I just feel like it's close to that. You can get by simplifying. All right, what's the time required to travel a distance h upon being released? Well, time, distance, it's kinematics. And we want distance. We don't have anything about speed. We don't care about speed. So it's the speedless kinematics, which is delta x equals 1/2 at squared plus v0t. We're traveling a distance h at constant acceleration that we'll plug in for later. So t would just be the square root of 2h over a, which would be the square root of 2h divided by A, which is m minus m g over m plus m. And I feel like I should simplify that one, just to get rid of the double compound fraction here. So this would be equal to square root of 2h m plus m divided by m minus m times g. Okay, kind of a gross expression. Determine the acceleration in the limit m gets much, much bigger than m. Justify why this is expected. So a is equal to m minus mg divided by m plus m. So if m is much, much larger than m, what does that mean? That means means two things. This means m minus m is approximately just the big mass, and the sum of the masses is also just approximately the big mass. So if m is much, much bigger than little m, that also means what happens if we just say the little mass is 0. So this means that the acceleration would be approximately mg over m, which is approximately g. And that should make sense, because if you have nothing resisting your driving force, it's essentially in free fall. So the small mass essentially does nothing to fight it, so we get pure free fall. Now we will just do the Atwood acceleration of all these different combos using our big box method. So first up, we have our standard Atwood we just looked at. We'll always assume that this capital M is larger. All right. So we have mg that way, we have mg that way. Those are the only external forces. So our system is going to go that way. So the equation for the big box method in each case is always acceleration is F net of the system divided by m total. So here, help minus hurt for the system. The big mg helps, the little mg hurts, and there's a total mass m plus m. Now that is actually the same result we got up here, right? It's just factored out with a g. All right, now we got some modified Atwoods, because they're not the original. So we'll big box it again. So here we have mg, that is driving my acceleration, right? We're going to go this way. And yeah, there's some forces here, but they cancel out, right? We got mg and normal force. So here, my acceleration is going to be help mg minus hurt, which is nothing, divided by total mass. So this is actually a simpler case because there is no resistive term. All right, now we got the ramp. So for the ramp, same idea. Box it up. So here we have mg driving us down this way. And we do also have another opposing force, but since it's on a ramp, it's not the full mg trying to pull me the other way. It's little mg sine theta because we're on a ramp. So this acceleration would be big mg helping minus little mg sine theta hurting divided by the total mass. Now we got a double ramp. It says assume the ramp angle beta is bigger. So here we get part of its weight pulling down, going this way. Here we have part of its weight going down. Smaller mass and smaller ramp angle means the alpha side is definitely losing. So the acceleration is just the helping component minus the hurting component divided by the total mass. So hopefully this gave you some idea of like the trend we see with these Atwoods. We're just finding what is driving you and what is resisting. I feel like this is all the main four cases where we have the pure double Atwood, where it's pure resistance. We have one term doing nothing. We have one term resisting on a ramp, and we have both terms on a ramp. So using that idea and no formulas, we have the same masses set up in four different Atwoods. So we have the same total mass and the same general setup. We just have both hanging masses, one hanging mass, one flat, one hanging mass, one ramp, one hanging mass, one ramp, but the ramp is steeper. So we want to rank the acceleration of each system. So really, we're just looking at the help minus hurt here. So first of all, notice the help force will be the same for all of these. The help force is the same in all four cases because we have a vertical 8 kilograms driving the system. Now we can look at the hurt forces. So for the hurt forces, we have a vertical hurting force, we have no hurting force, we have a angled down the ramp hurting force, so a partial hurting force because it's a component of weight, and we have a longer hurting force because it's a steeper angle. So if we were ranking the acceleration, blue wins by the most in system 2. And it wins the least in system 1 because we have the most resistance. And then we would accelerate lower in system 4 because there's a larger resistive gravity component. So the mass of each system is the same. In system 1, there's two opposing full weight forces. In system 2, there's a single weight force with no opposition. And in 3 and 4, there is a partial weight force providing the opposition with the greater, steeper ramp causing more opposition. Wow, that's a tricky one. But notice we don't need any numbers for this. I liked it at least. All right, that's basically everything I could do with systems.